right. Thank you all for coming today. Like I sometimes say, there are two kinds of philosophers. Maybe I should say two kinds of people. Those who believe in simplicity and those who don't. And as it should be obvious from my talk, I am in the first camp. I believe in simplicity. Now, I do think that many people implicitly assume simplicity was something similar in their theorizing or working about philosophical theories or physical theories about the world. Today, I want to focus on simplicity of physical laws, laws of nature. Such a kind of simplicity principle, and I think one that's crucial for understanding scientific realism. Okay, by the way, let me add that please feel free to ask clarification questions because many of these things to me are not very clear either. So feel free to clarify, and it's very much a work in progress. The short version of this is on archive, it's a preprint version, and the longer version I'm still writing, and so I'm eager to get your feedback on this project. Okay, let me start with a brief introduction. Physical laws are strikingly simple. Although there is no a priori reason, they must be so. It's not a priori that laws have to be simple or that they're guaranteed to be simple. It could be the case they're not simple. It can be complicated laws, time-dependent laws, space-varying laws, and so on. Now, I propose that nomic realists of all types, that include both Humeans, who think that laws don't govern, laws just summarize, and non-Humeans, who think that laws don't just summarize, right? Laws somehow explain in a robust sense. Whoever takes laws to be real and objective in some sense, right, as I explained later, should accept that simplicity is a fundamental epistemic guide for discovering and evaluating candidate physical laws. And I'll explain what I mean by fundamental, epistemic, guide, discovering physical laws, and so on. Okay. Now, it's kind of at a general level, I want to say that the proposal I have, the principle of simplicity I have in mind, is somewhat modest. It is a guide to lawhood rather than a guide to mere truth. And it can be comparative, right? L1 is simpler than L2, so on and so forth. It can be vague, might not be determining in some cases, can be partial. Doesn't render any judgment at all for some laws. Now, from certain perspective, though, it can appear epistemically immodest. My principle might be a version of what John Roberts calls the contingent synthetic a priori principle. I say that simplicity is fundamental epistemic guide to lawhood, but it's not guaranteed that laws are simple, so it's contingent. It's synthetic because it doesn't follow from definitions or logic alone that laws are simple. It's a priori because something that we have to presuppose before investigation, experiments, discovery, and evaluation. So the principle I have is, I think, is of this kind, contingent synthetic a priori. I don't think it's a problem, right? It's not a problem per se because we know we need something like it for the problems of induction. Hume, Goodman, and others, right? Why will tomorrow be resembling today, and why will other parts we have not observed be similar to what we have observed? Okay. Oh, here's Hume, and here's Kant. Okay. So my motivation for writing this paper are as follows. Simplicity is puzzling for everybody, I think, for nomalists, for non-nomalists, for realists, for non-realists, and so on. But I think there is one particular discussion of this that's relevant. One is this influential argument in literature that Humeans or Humanism has an epistemic advantage over non-Humanism regarding explaining, say, our epistemic access to the physical laws. I think that's not correct. The argument can be traced back to John Earman and John Roberts, maybe even earlier. But I think when we clarify the notion of simplicity and relevant simplicity in discovering of physical laws, it turns out that the advantage is exaggerated and may not even exist. And second, I want to clarify something that Charlie Goldsmith and I call epistemic guides for understanding physical laws. And that's a account we call minimal primitivism about laws of nature. It's a version of non-humanism in which laws really govern and really explain, but one in which laws are very flexible. They can take any forms. But why can't they take time-dependent forms? What can that be very complicated? They can, but we have epistemic guides for directing us, for searching the direction of simpler laws. And the relation to determinism and strong determinism. Something has been discussed recently by Emily Edlam and me and others in literature. We see that when we try to clarify what determinism, strong determinism might mean, it's very crucial to have this notion of simplicity in mind. Otherwise, anything can be deterministic. Any physical law can be deterministic. It's pretty trivial. And we think about scientific explanation and problem induction, we run into problems that are similar to the problems of simplicity. Finally, it is something new to me, but this is what I learned from Elliot Sober's work, and goes all the way back to Popper and earlier Bayesians like Rinch and Jeffries. It's called the problem of nested theories. It's pretty hard, actually, at first, to formulate a coherent way, probabilistic coherent way to talk about simplicity as a guide to truth. That's why I moved from guide to truth to guide to lawhood. And I regard this to be a natural move, because the way we think about the connection between laws and truth. Okay, so that's my motivations. In the longer version of the paper, I want to argue that simplicity is a serviceable and unifying principle. It vindicates a wide range of epistemic commitments about physical laws. Without this, normally realists face challenges regarding underdetermination, induction, explanation, and determinism. Accepting the principle of simplicity is a very small price to pay for getting a lot of benefit, namely being a nomic realist. But in the shorter version in this talk, I want to focus just on determination. But bear in mind that the project is eventually going to make contact with other topics as well. Okay, let me be a bit more concrete and define a few terms so that everyone can be on the same page. So let's call nomic realism, or to be a realist about physical laws, the following two conjunction of following two theses: a metaphysical part and an epistemic part, to do with the world and a knowledge of the world. Okay, first, physical laws are objective and mind-independent. More precisely, which propositions express physical laws are objective and mind-independent facts in the world. Doesn't depend on your beliefs or my beliefs. Doesn't depend on your preferences or my preferences. It's something that's in the world, right? So I think Weinberg had a saying that his experience with physical laws is like his experience with a rock. You can kick a rock can hit you, you can bump into a rock. It's like physical laws are objective, and something physical in the world is mind independent. Okay, that's one part of nomic realism. Very basic part, right? Second part is a bit more subtle. It's called epistemic realism. We have epistemic access to the physical laws. We can know what the physical laws are. If there are things in the world, facts in the world that are true or obtained, what if we can't know anything about them? It's not going to be useful to us. It's not going to be relevant to us. It's not going to be important for us to discover. But physical laws are not that. Physical laws exist, are true, and so on. But also, we think we can discover them. More precisely, we can be epistemically justified in believing which propositions express the physical laws, given the evidence that we will in fact obtain. Given the evidence we in fact collect, past, present, and future, we will be in a position to justify ourselves, epistemically justified in believing which propositions express physical laws. It's an optimistic position, but it's one position I find interesting and challenging to defend. That's why eventually we need simplicity here. So this, by the way, invokes in fact obtain. It's not that we can possibly explain or we can in a position to obtain, but it is that we in fact obtain. In nature, given the space-time manifold, we are particular chunks of the space-time manifold. And given the evidence we in fact collect, we'll be in a position to know the physical laws. If not, right, why care about physical laws? Why even think there are physical laws? Why think they're important for discovery? I think it's very important to focus on this version of epistemic realism. So if you know this literature on physical laws and humanism, non-humanism, you realize that this is somewhat stronger than the notion of epistemic realism people have talked about, for example, by Ehrman and Roberts in their papers 2005 and 2006. They say it's something more like we are in a position to obtain. But I am saying that we will, if in fact, obtain. I think this is the more interesting epistemic realism. Okay, to be more concrete, I focus on two versions of accounts of laws of physics, two philosophical accounts of what laws are, not what the equations, which equations are right, but what the equations are about, right? What the equations are lashing onto in the world. One is a Humean proposal, that kind of somewhat a weaker proposal of physical laws. The other is a metaphysically stronger proposal that laws really exist and constrain, the non-Humean proposal. Okay, the first is called the Humean best system account, or BSA. So you may wonder, what are the equations doing in the physical theory? Are they just facts? Are they something that's outside of the space-time manifold or other facts? On the Humean account, they are merely summaries, certain facts. So given a, say, space-time manifold or some kind of manifold, that is the world entirety for past, present, future. And maybe we're here in a Zoom talk, and there's all the time, there is. Now, they're just events that happen here, position particles, and field configurations, plus minuses, and so on. Maybe quantum states over entire state. In any case, laws are nothing like this. Laws are merely summaries of what actually happened in different parts of space-time. They are the axioms of the best system that summarizes the mosaic being the entirety of the space-time manifold plus the local distribution of matter fields, maybe even the quantum state. Optimally balances simplicity, informativeness, fit, and degree of naturalness, right? So the laws in the best system are merely some kind of very nice, efficient summaries of what actually happened in space-time. Okay, and the mosaic only contains local matter particle effect. Mosaic's complete collection of fundamental facts, and the best system supervenes on the mosaic. It's not extracted in the mosaic. When you have a mosaic, when you have what actually happened in space-time, you have the laws. You can derive the laws from the mosaic in some sense. Laws are not fundamental, they're not extra. The other view on the contrast is what Sheldon Goldstein and I call minimal primitivism, or MIMP. The idea that laws are not merely supervenient on the mosaic, or derived from the mosaic. Laws are on par with the mosaic. Laws are at least explaining the mosaic. Fundamental laws are certain primitive facts in the world, fundamental facts. There's no restriction on the form of fundamental laws. So we're flexible about the form of laws. They can be boundary condition laws or time-dependent laws and so on. But they govern the behavior of material objects by constraining physical possibilities. They're not derivative of the actual world. When you have the space-time, it's not complete yet, unless you specify what physical laws are. The physical laws and the space-time manifold together comprise the complete fundamental ontology, what there is in the world. Okay, so space-time manifold plus the laws. And laws explain the mosaic by constraining its physical possibilities. That's the sense in which we say laws govern. Now, to sharpen discussion, I'm going to borrow one section of my paper with Sheldon Goldstein. Let's suppose that given a mosaic C, a mosaic, imagine the space-time manifold, okay, four-dimensional manifold. A mosaic C, there's a unique best system whose axioms express fundamental law L. So think of L being the best system of C, with this being a function that maps a mosaic to its best system law. For any mosaic, it maps to a best system law, L, best system. Different mosaic might be mapped to the same law, but the same, one mosaic cannot be mapped to two laws. Okay, let us stipulate that for both BSA and for MIMP, for both laws accounts we talked about before, physical reality is described by a pair law and mosaic, L, C. So law and mosaic. Now for Humeans, law is not fundamental. For MIMP, for us, it is fundamental. It's one difference. For both, we must have that C is a member of omega L. What is omega L? Omega L is a set of mosaics compatible with L. So for given any law like F equals ma, you have many different mosaics compatible with this equation. Many different histories, solutions to this equation, say specifying some kind of Newton gravitational law, right? You have many possible solutions, or many possible worlds, possible space-time, possible mosaics compatible with this law. So omega L collects all the solutions, or all the mosaics compatible with L. Now we say that C is a member of omega L. This means what? L is true of C, right? So L is true in C. That's a sense in which we say C is a member of omega L. It's the interpretation we talk about laws and mosaic instead of models. So think of omega L as a set of nomological possibilities generated by or compatible with law L. Now, moreover, on both we have C is in omega L and L is true in C. But on BSA, we also have that L is BS of C. L equals to the best system of C. It has to be the best system of C. So this is a crucial difference with mean P. In a sense, all we need in BSA is C. L is not ontologically extra. But it does not follow that BSA has an epistemic advantage over mean P. You might think, okay, given the mosaics all we have, then we can only access the mosaic. So L is easier to discover on Humean BSA than on non-Humean mean P. That's not true. On neither account do we get epistemic realism for free. Why is that? Think about our epistemic situation, what we know, what we can gather. Let E evidence denote our total evidence consisting of observational data about physical reality. Let us be generous. Let E denote not just our current evidence, but also all past evidence and all future evidence about the universe that we will in fact gather. So think about a whole space-time manifold. And we are but a very small chunk of the space-time manifold, beginning of mankind until the end. We don't even do science for all time. But for this time, we'll gather evidence, E1, E2, E3. Eventually, maybe we'll be, gathering all the evidence we have for physical universe and call this totality of evidence E. Now, notice, does E give us a guarantee of what physical laws are? No. There are two features of E. First, E does not even pin down a unique mosaic, C. The different candidates of C, right? Suppose you keep this part the same, but you vary this part of the mosaic. There'll be no difference to E. The different candidates of the actual mosaic, they will yield the same E. After all, E is spatiotemporally partial and macroscopically coarse-grained description of C. Not only is this partial, but also it's coarse-grained. E is only a macro description of reality. You see a pointer points this. You see flash on the screen like this. You see some kind of macro properties. But they can be realized by different kinds of micro properties, microscopic trajectories and particles and fields. So E doesn't even pin down a unique mosaic spacetime. And E does not pin down a unique L, law of nature. The different candidates of L yield the same E. On BSA, this is an instance of the previous point on mean P, because on BSA, the mosaic determines the law, right? Different mosaic can determine different laws. On mean P, however, this is even clearer because the law can vary independently of C up to a point. As long as L is true in C, you can vary the set of possibilities generated by L independently of C. Hence, on BSA, just as on mean P, on both theories of laws, Humean and non-Humean, there's two versions, E does not pin down the pair L-C. Our evidence does not pin down a description of physical reality, law, and spacetime. There is a gap, a huge gap, I would say, between our evidence entails and what the laws are. Okay. That's a bit abstract, And let me go to a few more examples to bring out some of these ideas. The best examples of the gap are cases of empirical equivalence. There are other examples, more complex to construct, but the simplest ones are going to be ones of empirical equivalence. I am going to consider 3 reasonable algorithms for generating empirical equivalence. Reasonable in what sense? So there are discussion literature, and I think discussed very nicely by Kyle Stanford and others. I think one of them is a very nice book by Andrew Kukla, is a discussion of certain kind of algorithms, but they're very fanciful, very kind of sci-fi-ish, very kind of almost like Cartesian skepticism. They're not very, scientifically real. They're more like science fiction examples or evil demon skepticism. We don't have to resort to those kind of radical skepticism to get empirical equivalence. We can have empirical equivalence much more easily by using things, strategies, algorithms we have already seen in the literature on physical laws, in philosophy of physics. Now, I'm going to talk about empirical equivalence in a weak sense. I'm going to talk about empirical equivalence given actual evidence. So for 2 theories, T1 and T2, as long as they agree on what is actually the case, what is actually the evidence we have, then they are empirical equivalent. It's a weak sense of empirical equivalence. Usually people talk about empirical equivalence with respect to all possible evidence or possible data. It's stronger. It's okay. It's a notion of empirical equivalence. It's not the one we need. I need here for my argument, okay? It's another valid argument, valid notion of empirical equivalence, but it's not the notion I'm going to use in this argument. I'm going to use actual empirical equivalence. It's a notion for empirical equivalence. Okay, 3 strategies. The first one works for both Humean and non-Humean, and the second one is for non-Humean, and the third one is for Humean. Okay. First strategy, algorithm A. This is compatible with both humanism and non-humanism. So imagine we have a theory T, T1 equals to L MC, law and space-time. Now, if C can be decomposed into 2 parts, say C1 and C2, say particles and fields, right? So there are 2 kinds of material ontology, 2 kinds of stuff in the world. Particles that move, fields that permeate space-time. Both exist as in this T1. Then we can move one part of it into the laws package. Regard that as not something that exists, but something that tells particles how to move. Okay, given the physical reality, we can decompose this and consider an alternative theory, T2, which is what? L plus C1, comma, C2. So we move C1 from the category of things that exist in the space-time to the category of laws of nature. So this is the new law in L, T2 compared to L. In general, this will complicate the laws package. It's going to make it very complicated. But still, it's a possible theory. It's a possible law, and it's a possible ontology, a possible mosaic. Just C2 by itself. One example. So consider the standard theory of expelling electrodynamics, classical ENN, TM1. Call this TM1. Nomology, the laws include Maxwell's equations and Lorentz force law. And the ontology is standard ontology of Minkowski space-time occupied by charged particles, trajectories QT, and electromagnetic field Fxt. So think about in this way. You have a Minkowski space-time, you have a bunch of particles that move. Oh, sorry. Should probably draw curves like this. And you have a field on space-time that assign values to every point in space-time. That's TM1. Ontology is this, the purple part plus the green curves, and the laws of Maxwell's equation, Lorentz force law, telling this how to behave, which are the possibilities. The second theory is exactly like this, except I take away the fields. Oops. You have just the particle trajectories and no fields. What are the fields? The fields are going to be specified by a function in the nomology, the package of laws, the law of nature. So TM2 has what? TM2 has Maxwell's equations, Lorentz force law, and enormously complicated law specifying the exact functional form of fxt that appears in dynamical equations. The one particular solution to Maxwell's equation, the field configuration, specified by a law of nature. That's a new law in TM2. Now, we no longer have fields in ontology. What exists in mean cosmic spacetime is merely charged particles, trajectory that move. Okay, so only particles and no fields. Our evidence E, if we were to live in a classical universe, is compatible with both TM1 and TM2. Both theories are compatible with our actual evidence in such a universe. The outcome of every experiment in the actual world will be consistent with TM2, as long as the outcome is registered as some kind of macroscopic configuration particles, say the point position. Measurements of magnetic fields, electromagnetic fields can be registered as pointer readings, and pointer composed of particles, and particles give rise to macroscopic configurations, and you have readings of results of experiments, right? We can think of the new law in TM2, the law specifying the field configuration, as akin to a Hamiltonian function in classical mechanics. Well, there are disanalogies too, but what's kind of relevant here is it's interpreted as encoding all the classical force laws, except that specifying fxt is much more complicated than specifying standard Hamiltonian. Now, on this analogy, both fxt and Hamiltonian are components of respective laws of nature that tell particles how to move, how to behave. So we move part of the ontology to the nomology, the laws that tell the rest how to move. We have two theories, TM1, TM2. They're empirically equivalent. The only difference here is simplicity. Now, there are other differences too, but one difference is simplicity here. By the way, this might feel fanciful and contrived. I agree. No one has proposed this and endorsed this theory, TM2, but it is very much similar to debates in, say, the ontology of quantum mechanics, whether the quantum state, the wave function, is a field or a wall. There are differences here too, but there's kind of a similar strategy, similar idea here that's worth mentioning. Okay, that's the first strategy, works for both humanism and non-human. The second one is designed for MinP, for a certain version of non-Humean governing picture of laws. We can change the laws directly. Now, suppose the actual mosaic, again, is governed by some law L1. Say, here's the omega L1, set of mosaic compatible with the law L1. Now, C is a member of omega L1. Here's a very small change. Regard this omega L2, generated by some L2, as a set of models compatible with C, but it is different from omega L1. They have different sets of models. They disagree here and here. They agree here, right? So they're different sets, and L1 and L2 have different laws. Now, since E is a coarse-grained description and part of the description of C, E can arrive from both laws, L1 and L2. And moreover, there are infinite many such candidates for omega L2. So it's easy to generate empirical equivalence on this theory, on MinP. For example, let L1 be the Einstein equation of general relativity with omega L1 equals to omega GR, a set of general relativistic spacetimes. So here is omega GR, set of solutions to Einstein equation. Assume the actual spacetime, say C, is governed by GR. So C is a member of omega GR, okay? Consider L2 a law that permits only the actual spacetime, and it completely specifies its microscopic detail, with omega L2 being a singleton set, C. So L2 is a very specific, very strong, and very deterministic law that's compatible with only one model. It is called a version of a theory of strong determinism, right? It is compatible with only one model. Now, since our evidence E arises from C, is compatible with both L1 and L2. Even L2 is very strong, it is still compatible with our evidence because it predicts that our evidence will be the only kind of evidence we'll in fact gather. We can only gather. Yeah, right. So this thing in this thing called the exact detail of C, L2, sorry. L2 is much more complicated than L1. Even though they're both compatible with our evidence, L2 is much, much more complicated than L1. I mean, the Einstein equation is not simple to write down, right? But L2 is going to be so much more complicated. You wish that we don't have this law at all. It's a very radical kind of complicated law. Okay. That's the second strategy, working only for min P. Now for BSA, for humanism, we have to do something much more, a bit more subtle because on min P, on BSA, there's a constraint that L equals the best system of C. So we have to suitably change the mosaic to get a case of empirical equivalence. The mosaic is fundamental here. So we change the law by changing the mosaic. Okay, how do you do it? Suppose the actual mosaic is often described by some, so here's the actual mosaic C, and we have some actual evidence E in the mosaic. So this is the best system, L1 is the best system of C. Okay. Now we can consider a slightly different mosaic, C prime, such that it differs from C in some spatial-temporal region that's never going to be or was observed. And yet E is compatible with both C and C prime. How do we do it? We can, change this part. We change this part. Or we can enlarge space-time a little bit. Or we can cut space-time a little bit. As long as we keep E the same, we have a mosaic that's in general going to give us a different kind of law, best system. There are even many such candidates for C prime, whose best system L2 differs from L1, right? Even though E is compatible with all of them. So in humanism, we can chop out the mosaic or change the mosaic or twist the mosaic in some ways, in some small or large ways, depending on how we do it. That will give you a different best system. That will be empirically equivalent, yet distinct law. For example, let L1 be the Einstein equation of relativity, assuming the actual spacetime is general relativity spacetime. So C obeys Einstein equation. Now we can consider C prime such that it differs from C in only the number of particles in this region of spacetime in a faraway galaxy with no direct observation. Now, since the number of particles is an invariant property, we don't have to worry about the whole argument here. Assuming C is well-behaved, global hyperbolic, we're going to have determinism and can use that to deduce that C prime is incompatible with general relativity. Because in this region, got different number of particles from the C solution. So in L1 is different from L2, the best system, summarizing the slightly modified mosaic, C prime. Right, since C prime violates conservation number of particles, L2 should be more complicated than L1. Okay. Now, I've mentioned these algorithms to bring up the fact that we have empirical equivalence. But in those cases here, we discuss here, there's kind of a nice feature that is, they can all be broken. The type can be broken by invoking simplicity, at least it's simplest, right? Suppose we don't like complicated solutions or complicated laws. Because those laws are not realistic or physical or relevant because we only think about simple candidates, simple laws, simple theories. So what if we invoke this principle of simplicity? The three algorithms before can be answered by using simplicity. The motivation to justify preferences among empirical equivalents, say TM1 is better than TM2 because this is much more complicated laws, right? So consider following guide to truth. It's a kind of a naive version for simplicity. That is, simpler candidates are more likely to be true. If you've got a simpler theory, it's more likely to be true than the other theories. It's more complicated, even though it's more empirical equivalent. So this, I think, is underlying a lot of discussion literature regarding simplicity, regarding inferences, regarding explanation, regarding even Bayesianism. Now, there are many puzzles about simplicity. First, there are two well-known puzzles. One, the problem of precision. It's difficult to say exactly what simplicity is and how simplicity should be measured. Is it number of parameters, length of sentences, is it concepts involved, and so on. Second problem is the problem of justification. It's difficult to justify principle of simplicity in terms of epistemic principles. Why, in virtue of what, should we think that nature respects the simplicity principle? Okay. Now, those two problems do not show that it's wrong to rely on simplicity. They can be regarded as open research problems that might be answered in the future with better technology or better ideas of algorithm complexity and so on. Therefore, I think they're not fatal and can be answered, can be explored. However, there's a much more urgent problem. It's different from both. But because it seems to suggest that simplicity principle is incoherent probabilistically, and hence must be false. I'll focus on this issue below. It was first raised by Karl Popper against Rinch and Jeffrey's account, right? Rinch and Jeffrey, early 20th century, proposed an account for scientific inference relies on something like guide to truth. And Popper showed this probability is incoherent. And discussions in Sober and Schubeck and Henderson have made this point very clear in the literature. It can be seen as follows in a simple case. It's called the problem of nested theories, or sometimes called the problem of conjunctive explanations. Consider two theories with nested sets of models. So omega L1 is a subset of omega L2. So every member of L1 is a member of L2, but not vice versa, and a proper subset. So here is omega L1, outside is, omega L2. So omega L1 is contained within omega L2. L1 and L2 different laws. Now, you observe by the Venn diagram and by the probability axioms, the probability L1 is true cannot be higher than the probability L2 is true. Just smaller area. Think of area representing probability here, right? L1 cannot be more likely to be true than L2 is. L2 has to be more likely to be true or equal to probability than L1. So guide to truth cannot be right. Now, as an example, let omega GR again denote the set of models compatible with the Einstein equation. So, omega L, draw smaller. Omega GR, set of general relativistic spacetime, and let omega GR plus be the superset of this GR plus, with which is a union of omega GR plus a few random spacetimes that do not obey Einstein equation. So these are incompatible with Einstein equation. Now, this omega GR plus has both GR and non-GR solutions. Suppose there's no simple law that generates omega GR plus. Think of this as a disjunctive theory, disjunctive law. Either GR is true or something else is true. While the law of GR, the Einstein equation, is presumably simpler than that of GR plus. Einstein equation is simpler than the disjunctive law, say. The former cannot be more likely to be true than the latter. Every model of GR is a model of GR plus, and not every model of GR plus is a model of GR. So guide to truth cannot be right in this case. Hence, it is probabilistically incoherent to maintain that simpler laws are always more likely to be true. Not coherent. So the puzzle about simplicity is following. If simplicity is not a guide to truth, what is it a guide to? That's a big question mark that I had earlier this year. Okay, so let me report some of the results and ideas and tentative conclusions I've drawn from this project. I think the best way to think about simplicity, physical laws, nomic realism, scientific realism is as follows. I propose that simplicity is a fundamental epistemic guide to lawhood. Roughly speaking, simpler candidates are more likely to be laws, all else being equal. The principle solves the problem of nasty theories in a straightforward way, as I'll explain. And it secures epistemic realism in cases of empirical equivalence, where simplicity is a deciding factor. Okay, let me explain. By the way, my principle of simplicity is not the same as the simplicity criteria in the Humean best system account of lawhood. Think about best system account. Talk about the Mosaic, best system of the Mosaic involving simplicity and so on. It's not the same simplicity criterion. They play different roles. They might be different, same measures, but very different roles. They different kinds of principles. One is a metaphysical principle of what laws are, the Humean one. And the other, mine, is an epistemic principle concerning amplitude inferences based on our total evidence. To go beyond total evidence, what do we have to rely on? The simplicity principle is about that. Even if a Humean expects that the best system is no more complicated than the Mosaic, it does not follow that she should expect that the best system is relatively simple. She can only expect that the best system is no more complicated than the Mosaic, but not simple simplicator. Okay? There is no metaphysical guarantee on humanism that the Mosaic is cooperative. It can be summarized in a simple way. It can be unified in a nice, elegant way. So the Humean criterion of simplicity and the principle of simplicity I'm discussing here come apart and are different. Now, both Humeans and non-Humeans can be uncertain about the laws, and both need a new principle to justify epistemic realism. If Humeans are epistemic warranted in making such a posit, non-Humeans are too. So they are on a par in some way. Let me clarify the key notions: simplicity, guide, lawhood, epistemic, and fundamental. For simplicity, I don't want to insist there is a single measure of simplicity. There are many aspects of simplicity. There's, say, number of objective parameters, length of the axioms, algorithm simplicity, conceptual simplicity. They can trade off with each other. And hence it can be vague, because each one of them is vague and trade-off function can be vague. And it can be partial. We don't need a total ordering of every possible theory, from the least simple to the most simple, right? No, we can just have partial chains of simplicity orderings. And it can be comparative, right? We don't need a total number of assignments according to some kind of prior probability distribution, just like comparative judgments. L1 is simpler than L2, or L3 is simpler than L1, something like this. And moreover, it is going to be a guide, not a guarantee. As a guide, it should be fallible and maybe probabilistic. Given something being simple, it is very good evidence that it might be the law or a good law, but it's not infallible guarantee that it has to be the law or nature has to be simple. So simplicity compares something comparative and maybe probabilistic. Say other factors being equal, if A is simpler than B, then the fact that A is a law has higher probability than the fact that B is a law, where this represents the comparative simplicity criterion, and this represents is a law, which is an operator that makes a proposition to one about lawhood. And moreover, we can have overall comparisons that take simplicity as one guide and informativeness and naturalness and maybe unification and maybe other factors together as guides for lawhood, where this is one of the many guides. Again, you're going to have some kind of function to trade off one to the other. So given that kind of trade-off, we have overall comparison. Say if A is overall better than B, then A is law has higher probability than B is law, right? Where this represents overall comparison. Okay. Okay, so here is another crucial part, and one of the key upshots here is that we want to have an epistemic guide not to truth, mere truth, but to lawhood. We call the early example of GR and GR plus. And omega GR plus. Two laws have nasty models. Even though we think that Einstein equations will like to be a law, it is less likely to be true than the law of GR plus. The two are compatible, see? I suggest that the simplicity, what simplicity selects is not truth in general, but truth about lawhood, where a certain proposition has a property of being a law. You have some equation, say F equals ma, some other equation, F equals ma, many complicated stuff. These are both equations can be both true of the same world, but one might be more likely to be a law than the other. So let us assume that fundamental lawhood is factive, which means that if something is a law, then something is true. So if P is a law, then P is true. So lawhood implies truth. Assumption given. This is something granted on both BSA and MP. However, truth does not imply lawhood. If something is true, does not follow logically that it is a law. So truth does not imply lawhood, but lawhood implies truth, which means LP is logically inequivalent to P, and LP logically is stronger than P, right? So they're two different propositions. And this is the key to solve the problem of nasty theories. How so? Again, guide to truth leads to probabilistic incoherence. If L1 is simpler than L2, guide to truth tells us that L1 has higher probability than L2. That cannot be true when we have omega L1 being a proper subset of omega L2, because action probability tells that L1 has less or equal probability with L2. The two are incompatible. But guide to lawhood avoids this. Now, if L1 is simpler than L2, guide to lawhood tells us to infer not this, but this. That L1 being a law has higher probability than L2 being a law. And this is compatible with L1 has less probability than L2. So L1 might be less likely to be true than L2, but L being a law has higher probability than L2 being a law. Now we know that LL1 implies L1, and therefore this has lower probability than L1. So you have what calls a probability chain, inequality chain. The lowest probability is L2 being a law. The highest probability is L2 is true. But in between, we have L1 and L1 is law. And this is, I think, a simple solution to the problem of nasty theories. And I think very natural in the context of physical laws, because we know that some equation being true is different from some equation being a law. Now, why should we take this guide to lawhood to be epistemic, relevant to knowledge, evidence, understanding, justification? Well, it is something we arrive at by reflective equilibrium. You think about all the things you want to justify, want to believe in, want to commit to. It is one posit we should make to justify epistemic realism about physical laws, right? To be a nomic realist, you want to be epistemic realist. To be an epistemic realist, you want to pick your favorites among the imperial equivalents. How do you do it? Simplicity in those cases. TM1 better than TM2. The identity equation better than the Einstein equation plus a bunch of random models. So it is here we see that epistemic realism comes in, reflecting equilibrium that will lead to the best to have this kind of coherent set of beliefs is by positing simplicity as an epistemic guide, not pragmatic guide only. It might be useful for making predictions, evaluations, but also it's epistemic, having to do with justification and knowledge, understanding. So for our preferences to be epistemic justified, the principle of simplicity should be an epistemic guide, not merely a pragmatic guide. Okay, fundamental, the last part. What about reductive approach to simplicity? Can we reduce simplicity to something else? Say probabilistic theories, convergence results, topology approaches, or maybe archaic information criterion proposed by Forster and Sober as a way to understanding simplicity. These are very useful approaches, but they're not going to be helpful here. Here we're talking about issues of empirical equivalence. And those approaches, reductive ones, at best, if they succeed, right? And there's a question of if, right? If they succeed, they're only about empirically inequivalent proposals, laws, and theories. It's not going to be helpful to our cases. Does guide to lawhood follow from metaphysical posits of bad system account? No, again. What counts as actual bad system on BSA may differ from what we should accept as bad system according to guide to lawhood. There's no inconsistency because which laws actually obtain can differ from which laws we should actually believe in. It's compatible with humanism that the Mosaic is such that it is very minimal, and laws, the best system, may be very complicated. But the human might be inclined to posit the Mosaic to be such that it contains more stuff, so the best system is more simple. So the two simplicity criteria are actually coming apart in this case for humans themselves by their own lights. So you see that BSA doesn't entail the guide to lawhood. Hence, defenders of BSA are in a similar epistemic position as defenders of MIMP. And this point is worth emphasizing because according to the influential argument due to John Earman and John Roberts from 2005, and later by Roberts 2008, humanism has an epistemic advantage over non-humanism because the former offers better epistemic access to the laws. They think that humans, right, the Mosaic is all we can empirically access anyways for both humans and non-humans, which laws are supervenient for humans. But non-humans postulate facts about the Mosaic, they're in principle empirically undecidable, like modal facts, governing facts, constraining facts. They can freely vary from the Mosaic. The Mosaic for them fixes the laws in a way that reduces the degree of freedom in the laws. So they regard this as an advantage of humanism. But if I'm right, we should question the epistemic relevance of the argument. The Mosaic is there, true, but we never, in fact, occupy the position to observe everything in the Mosaic. We are at best in a small chunk of the Mosaic. For our entire time of existence, humankind will never occupy every part of the Mosaic to observe everything directly. Most of our knowledge of the science, physics, space-time laws are very much inferential, indirect, and based on our observations of local or current environment. And everything we'll actually observe only be a subset of what actually will happen. Although the evidence E will never exhaust the entire Mosaic C. The Mosaic is just too vast. If both humans and non-humans need to accept independent substantive epistemic posit in order to ensure epistemic access to the laws, there's no real advantage on humanism. The reason we have epistemic access to the laws is by appeal to the new principle of simplicity, which does not follow from the metaphysical posits of either humanism or non-humans. Both humans and non-humans have to posit some kind of principle of simplicity beyond the metaphysical posits to get to laws. So in this sense, humanism and non-humanism are epistemically on a par with respect to the discovery and evaluation of laws. In conclusion, nomic realism can be epistemically risky since it requires amplificative inferences to go beyond what empirical evidence guarantees. Right? It's risky, but many things are risky, right? However, the risk is no smaller on humanism than on non-humanism. When you decide what the physical laws are in a vast space of possible candidates, based on our finite and limited evidence about the universe. The principle of simplicity, its fundamental epistemic guide to lawhood, it encourages us to look in the direction of simpler laws. Right? There's so many ways to search for physical laws. We do prefer, and I think we should prefer, simpler laws. And this principle vindicates nomic realism in cases of empirical equivalence generated by the algorithms and avoids probabilistic incoherence when we have nasty theories. Simplicity is not a simple thing, but from the analysis, we can conclude that its connection to lawhood is much tighter than the connection to mere truth. Rather than saying that the simplicity is the seal of the true, simplicity should be regarded as an epistemic guide to the laws. Okay, that's the end. Thank you for your attention.
All right, everybody, welcome back. We're going to get started with the discussion and question and answer period now. We'll use the remainder of the hour for that. Usual rules apply. I'll ask you to use the hand raising tool if you'd like to ask a question. This discussion and question and answer is being recorded. If you'd like to ask a question anonymously, you can send me a private chat message and I will read your question with your name attached. I'll go in the order in which hands are raised. but I will try to prioritize people who have not yet asked questions. So if you have more than one question, I'll ask if possible for you to go to the end of the queue. I always have a lot of questions. I have a long list, but I prefer to let our guests ask questions first. But if we run out of questions from the guests, Eddy, don't worry, I have plenty to ask.
Sounds good. Thank you.
All right, so please feel free to use the hand raising tool if you're ready. And I see a hand now from Barry. Barry, please go ahead.
Hey, Eddy, thanks.
Hi, Barry.
Hey, Eddy, how are you?
Good. How are you?
Hope you can enjoy the sun.
Thanks. We had rain last night.
Oh, well, it's sunny in New York, but it's going to be a storm. Anyway, it was very interesting. And I have a couple of questions, I guess a question and then an issue, sort of. Really just two, I guess the two issues. One is a very tiny one. Your argument that simplicity as a guide to truth is incoherent really depends on thinking that all possible theories are on the table. And so if there was a prior probability distribution which removed some of the theories, it still might be that the simpler theory is more likely to be true. That's just a remark about how your argument depended on that. The more,
I see.
Okay, I mean, that's, I think what it's just, you agree with what I said, right?
Let me think. So there's discussion about the problem nested theories in the literature. I think go way all back to the 70s and 80s. And people have talked about this, which basically rule out those problematic cases by hand, by fiat. And would that be a solution to the problem nested theories? I think maybe not a consensus, but one school of thinking is that it's not going to be a solution in the sense that in some cases we do have nested theories. So in the space
right, I don't think it's a general solution. I was just making the remark
I
that
see.
if, for example, there were a bunch of sentences that you wondered which ones are true and which ones aren't true, you could use it could be a guide that the simpler ones are more likely to be true if you didn't have on the table sentences which are logical implications of the ones that are more likely to be true. Just a very simple, just an observation.
Right. I see.
Okay. Okay, but the more interesting issue concerns the issue about Humeanism, where your view seems to be that the Humeans don't have any advantage with respect to the idea that simplicity is a guide to lawhood. And I don't really see that. On a primitivist view, whatever evidence you have, that evidence might be for what the fundamental world is like, but the laws could be anything at all, including incredibly complicated laws, as far as the metaphysics of primitivism is concerned. But for Humeanism, what evidence you might have for what the Mosaic is like, or what the fundamental properties are like, is one thing, but the laws have to be simple. That's just part of what it is to be a law on the Humean account. That seems to me to give the Humean account an epistemic advantage. Because if we could say that we have some good reason to think, maybe even on the basis of simplicity, because maybe our guide to what the Mosaic is like is also a matter of simplicity. That's not Lewis's view, but it's a view that I have. Then simplicity is sort of built in to what the fundamental properties and the laws are. And so simplicity is a guide.
Right. So I do think that there is kind of a natural extension from the simplicity criteria in the metaphysics of lawhood, or BSA, to one about epistemic principles, about what the mosaic's like. But I don't think that it follows from the metaphysics, right? Given that the mosaic is what there is, and given that laws are not going to be more complicated.
Not exactly right. The mosaic is what is fundamental from what there is. And that itself might be something that's determined by the best system of the world.
Right. So if you have this, the more package deal type of account like the one you propose, right, then Yeah, so we have to reformulate this argument to see how it applies to package deal account. I think the argument might still arise, maybe take a different form. But I think I was mostly making this argument in context of, Humean BSA versus non-Humean accounts of laws, primitivism, or things like this. But PDA, the package deal account, I think, will have a similar kind of issue regarding, say, whatever there is given to us, it's mind independent, right? If there is a mind independent part, a contribution from the world, then that part is not up to us. And that part can vary wildly in time and in space, in all kinds of complexities. And that will introduce complexity to the entire laws. So I don't think the package deal account guarantees simplicity of physical laws.
I think it's probably better for us to pursue this, just me and you,
right,
later. But I think I disagree with the last thing you said, just to register that. We should pursue it.
Right. I'm very interested in this line. So yeah, let's talk about this. Thank you, Barry.
I had a quick finger on that, and I know that Noah also has a hand up, but if I can just quickly follow up on that. So I was not entirely clear how this question of incoherence, how it is a problem for best systems accounts, generally speaking. My understanding of best system accounts is that they're not always looking at the assignment of laws to mosaics as a probabilistic exercise. So yes, it may be true that in some sense, you could have some sort of nesting going on with you have law 1 and you have law 2, and law 2 contains a larger set of possible mosaics, and maybe in some sense that means that that there's some epistemic evidentiary probability that law 2 is correct. But I think in a lot of best systems accounts, they would still say, well, that doesn't matter because one of my criteria is simplicity and L1 is simpler, and therefore I prefer that. Right? It's not just a question of what's the evidentiary probability that it's true. So I guess I wasn't entirely clear on how some of these challenges to primitivist understandings of laws applied to best systems accounts generally. I think my question is somewhat related to Barry's question, although I'm not 100% sure it's exactly the same. There is a certain probability that my account is nested inside of his, so I'm not sure.
Thank you, Jacob. So it's a good question. Let me clarify. So if you think that Humeans in the business of saying what is the best system, we can say, okay, what is probability 1, right? And what is probability 0? So there's only one thing with probability 1, namely the true best system. Yes. But then the problem becomes even worse when it comes to nested theories, because nested theory says the probability of the nested one, the bigger superset, cannot be lower than the probability of the subset. So if this is true, then that is true. Then the question is, what is the right best system, right? So there's kind of a logical entailment problem here. It's not even probabilistic. So what the Humean should say is that simplicity is a probabilistic guide to lawhood in the case of logical entailment, and in the case of, say, something being the clear best system of the mosaic, then you should have probability 1 being the best system, right? So it carries over when you think about, okay, replacing the best system versus law. And now I think the Humeans are in the same business of discovering laws. They're not given the whole mosaic. They have to guess what the mosaic's like. Now, they're not going to guess the mosaic's like by just kind of inferring other parts of the mosaic like the same part of the mosaic. No, they're going to have global laws of the entire space-time, which might include black holes, which inside is very different from what currently happens on Earth. So the patterns of events on Earth and what happens in the black hole are very different. So it's not uniformity of the mosaic that's doing the thing here. It's more like the simplicity of the best system. And making that posit is kind of making a restriction on possible mosaics one's considering, given our evidence so far. So I think I'm making this argument on both sides, non-Humean side and the Humean side, and I try to be neutral regarding how I set up the argument. So I try to be even-handed here. But I'm open to see how other people are thinking about this. That's very helpful.
Thanks. I want to make sure we get to our next question. No, please go ahead.
Okay, unmuted. Well, this was fascinating to me because, well, I'm very attracted to the idea of simplicity as a guide to truth, and simplicity as a guide to lawhood strikes me as very counterintuitive. But so first of all, I'm really intrigued by the nesting argument. And when you were discussing it, giving your general relativity example, I was thinking, well, how are you going to get any laws generating omega GR plus? And then you said, well, you could use disjunctive laws. And that jumped out at me as something very strange, because I would never have really thought that physicists or even philosophers are really interested in these disjunctive laws. And I just wonder whether the argument depends crucially on that. Are there other examples you could use which don't require disjunctive laws?
Good. Yeah. So my notion of lawhood is pretty flexible. So I allow for disjunctive laws, particular laws, time-dependent laws, and so on. And I don't see any good philosophical arguments on the non-Humean side against this kind of disjunctive laws. But I do think that this is very strange is because probably we have the intuition that laws should not be disjunctive, or laws should not be too complicated. So the two kind of intuitions might converge that we might have this preference for simple laws, which might by itself select those laws are not so disjunctive. So another example is that think about time-dependent laws. Say there is some law that's applying in one form at one epoch, and another form another epoch. That's kind of disjunctive, but we think about, say the Big Crunch or the Big Bang, maybe that can involve some kind of laws. So I don't want to have a theory of lawhood that's going to be so strict and so demanding that's going to prevent us from exploring possibilities of thinking about the whole universe.
I can see that time variable laws seem disjunctive, but the kind of laws that you were looking at seem to be disjunctive in a sort of far worse way. So I wonder whether,
So disjunctive in the worst way, do you mean like logical form? Because a logical form can be equivalent to a non-disjunctive law, just have defined some kind of
predicates. You can do
predicates.
logical tricks with it, but what I'm trying to sort of work towards is a way of kind of stipulating that what the kind of laws you're interested in are non-disjunctive in a certain way.
I see.
I would like to be able to say that they're non-disjunctive in a way that allows this temporal variation. So that would require some work. But it just seems to me as if I'd like to hold on to simplicity as a guide to truth. And this seems to me to be, if this is the only way that the nested argument works through disjunctive laws, then I would find there's something very fishy about it. And I would hope to get around it with some kind of stipulation as to what laws can't be disjunctive in a certain way. But just
hold on 1 second. Can you, so on the disjunctive part, what about conjunctive laws? Not by disjunctive, by multiplying with more models, but conjunctive by restricting to more models. Do you think that would be weird too? To say a single model of the universe?
I'm not so sure about that, because I can imagine that you'd have laws that contain conjunctions of variables in them. So I would think that I would expect something like that to be okay.
But disjunctive is not okay.
No.
But then in this case, we have two laws, for example. So I have some deterministic law, say, compatible with only one model. From this perspective, the original law has many models, which will be disjunctions of this one with other models in the universe. It's equivalent in terms of set of models. So this might be too strong, might rule out all possible laws. So this preference for disjunctive laws might be too strong such that it can rule out all possible laws we're investigating.
So wait a minute, I didn't quite follow that. Are you suggesting now a reason against disjunctive laws? It sounds as though You
No,
weren't.
I'm giving a reason to not restricting ourselves to non-disjunctive laws, because many laws, maybe all laws are disjunctive in some sense. Even
Yes,
Einstein equation might be disjunction of.
matter of the sense. It's just that the kind of the laws that you would need to capture omega GR plus would be so unlike just general relativity. So it just seems to me as if there might be a way of saving the principle if one goes with a more intuitive account of what the laws are. And certainly, I don't think physicists have ever really been interested in this. And when one looks at the best systems theory, I've never seen anyone advocate something with a rather radical disjunction in it.
What about different values of cosmological constants? That would be disjunction possible theories of GR, right? And then we prefer one of them, but we don't think it is impossible to have a theory that allows different cosmological constants.
I'm not sure. That strikes me as a bit incoherent. I can't quite see how it would.
I was not saying in one universe things are different values of the constant, but say different models with different values of cosmological constant.
Yes, I just find this effort to find a single law that's going to capture very disparate kinds of models rather strange. But just tell me again, is it absolutely crucial to your argument, to the nesting argument, that you allowed disjunctive laws? Are there any examples that don't?
Well, by definition, the superset is a disjunction of the subset with some other entities, right? So logically is equivalent to disjunction of that. The question is whether you have a simple description of the superset that's going to be not so gerrymandered different parts, but unified in some way by some general principles.
Okay, well, I'll rest on this one.
Okay.
And maybe I'll tackle you on
the
intuitiveness, the lawhood.
I have a quick follow-up to that question, if it's all right. So it wasn't clear to me why, if you have L1 and you have L2 and L1 is nested inside of L2, it wasn't clear to me why L2 was necessarily less simple than L1. And I can think of at least two counterexamples, one that was in your talk and also one that's a little more broad. So if I write down, let's say I have a quantum field theory and I write down a specific Lagrangian and I say, okay, my Lagrangian is going to have these 5 terms in it, these 5 intricately selected terms.
Yeah.
Or I could say, well, that's interesting. Those terms all share certain symmetry properties. So I'm going to take an effective field theory point of view and just say that I have a quantum field theory and I'm going to impose some symmetries. And now the Lagrangian can be any set of local terms that share those symmetries. Well, it seems to me that this new effective field theory is a more, contains more models in it. Its set of mosaics is going to be a superset of my old set of mosaics, but it's also simpler to specify. In fact, you mentioned Steven Weinberg at the beginning of your talk, his mantra, right? That you should always pivot to simpler, more symmetry-defined quantum field theories, effective field theories. And then they're both simpler and they're more encompassing. And the cosmological constant example you gave is actually a good example of this. Although, pinning down the cosmological constant in connection to symmetries is not fully understood. Allowing arbitrary cosmological constants is more symmetric than picking one particular cosmological constant.
Right.
Declaring, its value is exactly, putting in the Lagrangian, the value is, 0 point and then 120 zeros and then something. That seems like that seems less simple than just saying it could have any cosmological constant we don't know.
No, you're exactly right, Jacob. So L2 doesn't have to be more complicated than L1. I'm saying that there are cases where you go to a superset, it's complicated than L1, but not in every case. So think about the tautology, which is a superset of every theory, right?
Right. And of course, you had the super deterministic example where
strong deterministic. Strong deterministic. Sorry. You have the strong deterministic example where you specify the laws so precisely that in fact you just had a singleton set. Clearly, that's going to be contained in lots of. This was the other example. Perhaps it can be even Right, that's right. So all the disjunctive laws will be simpler than that one, hopefully.
Right.
But in some cases, maybe not. Maybe it's some kind of, say, aberration one calculus or quantum cosmology or some kind of proposals might be such that the strong determinism is simpler.
Right. I figured I just misunderstood something.
Yeah, I should have clarified. Thank you.
Yeah, this is very helpful. All right, my apologies. Before I get to more questions from people raising their hands, we have an anonymous question that was sent to me by a chat. Thanks a lot. I really enjoyed the talk. I'd like to know if the mere fact that a theory is true for a mosaic does not entail that the theory is a law, then what else is needed to justify a theory to be a law, or what are the basic properties of a law in the definition of the word law?
Good. This depends on humanism and non-humanism. For humanism, the definitions of lawhood come from the Mosaic. There is nice properties or tendencies about the Mosaic that are true about the Mosaic. Say simplicity is one of them. So for the Humean account, simplicity is part of the definition of lawhood, even in particular Mosaic. It's conditional, right? But it doesn't follow that it's unconditionally simple in the sense that given what we observed, the laws got to be simple. That doesn't follow. It has to be some extra principle, as I argue, this extra simplicity principle, or how we think about laws for the whole global spacetime. For the non-Humean part, I think people don't talk about simplicity that much. Maybe Shelley Golson and I talk about simplicity in our paper. One reason is that we want to emphasize simplicity in our conception of lawhood, not as a definition of laws. There's something that's very closely related to lawhood, almost like a high probability correlation or some kind of strong evidence for lawhood. But on our notion of lawhood, we think of laws as governing or in addition to the Mosaic, as explaining the Mosaic, in the sense of constraining what's physically possible. So F equals MA, it's not a mere summary of the Mosaic, but something that constrains what's physically possible given a classical spacetime. The trajectories are admitted as physically possible. And in that case, it is more in this notion of governing that we have this notion of lawhood. But simplicity is a very strong and useful and very important evidence for lawhood. Without the simplicity, we have no way to discover what the laws are, which is completely blank. And this might give impression to some people. I think that non-Humeans has a harder task of explaining why laws are so simple, or why we believe laws are so simple. But I do think that the argument is not so clear-cut. I do think that maybe the evidentiary burden is not on non-Humeans, it's on both Humeans and non-Humeans. We have to assume the world is cooperative, that we can do induction and inference beyond what we directly observe. So in the end, the way we do empathic inferences may be based on this principle of simplicity about lawhood. Given this, we can derive relative uniformity of Mosaic from this, say not complete uniformity. That's going to be a very uninteresting world and maybe unphysical, but some uniform and simple principles underlying everything we observe. Even black holes and us are governed by the same laws. In that case, the simplistic physical laws give us a reason to expect what happened in the black hole may be very different, but still predictable or understandable by us who are living outside the black hole. It's a great question. Thank you.
The next hand I have is Nanxing.
Yeah, thank you for the very clear talk. I think I have two
Nanxing.
questions, and I think both of them are partly answered by your last reply. So you mentioned that you make a distinction of what is lawhood and what is true, right? And you also mentioned that there's a difference between what we should believe is the law and what's actually what the law actually obtains. But then I think that somehow put a more burden on the non-Humean, because in that sense, what gives us the commitment to such a lawhood, right? So as for Humeans, the simplicity in the lawhood, as you said, comes with the definition. But if you believe that what we should believe as law there's still something different of what actually is a law, but what actually is a law is still has to be simple. That seems to be more burdensome for non-Humean. So yeah, so that's one question. And the other question is also related. So so you seem to have the view of the lawhood as to be cover the entire mosaic, right? But if you think of lawhood as just have their scope and resolution, so in that sense, I think Humeans still have a better argument for the epistemic advantage of law.
Oh, you mean like local laws for our actual space-time
Yeah,
region?
in a sense, I think it will touch the problem of induction, as in from our observation, from the evidence, all the evidence that we can possibly gather, to and the laws that we infer to, what is the scope and resolution as to what the laws says that we. So I think from this view, the Humean have a better account of the scientific practice, whereas the non-Humean seems to need something more a priori to establish the kind of lawhood that you believe.
Okay, thank you, Nancy. That's very good question. Let me start with the second question. I think I'm assuming the laws are supposed to be universal in scope. They might have time dependencies, space dependencies, and variations in some regions and others. But I'm assuming that the task of scientific discovery and evaluation and inferences are about, laws of the entire reality. So if we only have restricted domains or restricted scopes of laws, that might require different arguments or different discussions. So as a second question, this first question, I think non-Humeans might have a better way of explaining why laws should be simple than Humeans do, but a different argument. But just may say that on my account, neither Humeans nor non-Humeans are going to claim or should claim that laws have to be simple. It's not guaranteed fact. It's not necessity. It's not something that we should expect with certainty. It's more like, at most, probabilistically, a high probability fact. And it's a fundamental fact. So for both Humeans and non-Humeans, they have deposited this as a fundamental epistemic principle. Not explained further by anything else. As I said, this does not follow logically from Humean epistemic account, doesn't follow from the BMP. It's logically independent. So I don't see how Humeans have a better explanation for this epistemic principle of simplicity. And non-Humeans.
Yeah, Humeans can say this is a pragmatic, this is what we prefer.
Well, if that's enough, then non-Humeans can do the same. But I was assuming both Humeans and non-Humeans are nomic realists, and they hold on to epistemic realism. If Humanism doesn't latch onto nomic realism, then it's a different kind of argument. And that's why we kind of want to start off with our discussion by making some assumptions. Of course, if the assumptions don't hold, we have to think about various pros and cons, different factors coming into play. I do think that if that's the place that Humeans have to retreat to, that will be a pretty big cost. But of course, I think many Humeans want to hold on to epistemic realism.
Okay, thank you.
Thank you.
Hey, so Gabriel, you have the next hand.
Hey, Gabriel.
Hi, yes. So I have a completely different line of question. I'm basically going to your original claim that there is no a priori reason to for simplicity.
Yeah.
And to me, in physics, we actively go and look for simple systems. If you think of an electron as a simple system, it's not something that you just wake up and see in front of you. It's something that requires a lot of effort first to know that it exists, then to isolate and manipulate and so on.
Yeah.
And even like things like isolation and determining and so on are things that we desire when we set up experiments. I mean, if you're building an accelerator, if a train passes by, there are vibrations that messes up your experiments. So you have to take care of this. then of course you find that that the laws, are about simple systems and are about things that are isolated and so on. But I worry that it's like the practice that we have, in experimental physics, because other subjects don't have that luxury, right? If you're studying economic system, if you're studying a biological system, you have to get, the system is already cut for you. In physics, you go and look for things that decouple well, that can be isolated and so on. And so to me, like naively, I would say that that's already a motive, a reason why sort of physics privileges this.
I see. So in experimental design already, we presuppose simplicity. So we get simplicity or simple mechanisms or principles out of it. That's not surprising.
Right.
I see. That's interesting. Yeah. So the question is, why do we presuppose this locality or effect isolation and so on? Is it justified? So it's going to be a similar kind of question, I think, because what if nature is so radically non-local, not just quantum non-locality, but also all kinds of, effective non-locality, that there's no shielding or isolation or control of any local subsystem. But by doing this subsystem, we kind of, maybe it's kind of, there's an evolutionary argument that we experience things in such a way that we kind of assume this can work. But then that's kind of going back further, right? What is already evolution, and should we think that evolution is holding globally and is aiming as a true beliefs or only survival enhancement? So yeah, that's very good. I think the question of simplistic physical laws really is, I think for me, heart of a realist perspective on science. It's one entry point. It might be equivalent, maybe even better, or other ways of thinking about scientific enterprise that presuppose different principles. And if there is, that'd be great. We can have different meta principles of science that develop and see which one is the best reasonable, effective regularization of how we think about science itself. Thank you.
Thanks, Logan. I have you next.
Hi, Logan.
Hi, Eddie. Thanks. This was really fascinating. This is maybe partially a follow-up on one of Nanshin's questions. I wonder about laws that might be contingent or only applicable in certain situations that might not hold,
right?
And in my view, that would include essentially all of the laws of chemistry. Like there was no a few moments after the Big Bang, there was no chemistry because there were no atoms or molecules, right? So like anything that we would call laws within chemistry, or think of biology, we talk about Mendel's laws, like presumably any laws of biology, as far as we know, would only apply for Earth biology. There, you could imagine other kinds of biology, which would have perhaps other kinds of laws. Right. But, I realize this is, philosophy of physics seminar, but I think just wondering about, but even within physics, right, laws like baryon number conservation or lepton number conservation, which are, those are really simple laws. Like it's really simple to state that as a law. And yet we believe those are probably contingent laws that don't actually apply at very high energies. So, and in fact, the more complicated versions are sort of more difficult to state clearly, perhaps. So I wonder about, sort of contingent or laws that may not, hold universally, and how that fits in.
Yeah, good question. So I'm focusing primarily on fundamental laws of physics. The laws that govern will often describe the entire universe. But I think the proposal here might be compatible with similar proposals for effective laws, special science laws, laws in other disciplines or other regimes. And in that case, as long as I think the evidential set is smaller than the full set of facts in the world governed by those laws, the argument can carry over, maybe not as simply, but maybe with some modification. Say in the case of chemistry laws or biological laws, they only hold for certain kind of regimes after the Big Bang and some kind of controlled, stable environments. And in that case, perhaps we can imagine all the possible situations that may realize that regime. not governed by any law. Just think about a priori all possible regimes. And then we can think about the current laws of physics, so current laws of chemistry and biology. Do they have to hold given our evidence? And if not, what other possible laws can there be? Different, maybe more variables, maybe more elements, maybe more interactions. We don't want to posit those kind of superfluous stuff. And perhaps it's justified on simplicity grounds too. Perhaps some other principles. So one interest of mine is to see, okay, discussions about mechanisms in biology and causal networks in social sciences, are they all justified in some way by simplicity principles? Or are they, free to posit any superfluous variables they like?
Thanks. I think that's helpful. So you might imagine, in this set of all possible circumstances, let's imagine taking a subset that applies only in whatever situation
Right.
laws of chemistry or the laws of biology are taken to govern, and then within that subset, you can apply a similar analysis.
That's right.
And search for simplicity. I mean, I do think if you look at the history of biology, the many of the breakthroughs have been sort of searching for simpler laws rather than just having sort of a description of lots of facts,
Yeah.
without any governing principles.
Right.
And so I do think that,
Mm-hmm.
right, exactly, like searching for sort of common phenomena that
Right.
underlie lots of different, seemingly disparate, unconnected
Right.
observations and facts.
Right.
So there is, I think there is something there that's helpful. Thank you.
Yeah. I'm very interested in this because there's discussion about laws of biology, or especially in biology. Do they appeal to simplicity? So Eddy has been working on this for many years, and he's been working on the common cause principle. Is it similar to simplicity criterion, and is justified by something else? So it's a very good area to look into. I want to look into next. Yeah.
Great, thanks. So I don't see any other hands, so maybe I'll go to one of my questions.
Sure.
I was wondering, so you mentioned in one of your slides this notion about the in the Humean account, the notion that the Mosaic might not be cooperative. I was wondering if you could elaborate a little bit on that, because I had potentially some questions about that, but I know it went by a little quickly.
Right.
Could you just elaborate a little bit on what you meant by the Mosaic potentially not being cooperative? Right.
So I was imagining that Humeans usually assume that induction works, and laws are probably simple, and the best system is not going to be too complicated because the Mosaic is going to have enough structure to maintain a nice unified system. All those principles are going to be principles about the Mosaic, assumption about the Mosaic, right? And certain kind of mosaics are not going to be helpful to induction, maybe counter-induction, and certain kind of mosaics are not going to be helpful to assuming that it has enough structure and so on. So various kinds of standard arguments in philosophy of physics, for example, that Humeans and non-Humeans make are going to be assumptions on the Humean side on the cooperation of mosaic, whatever that is. So that's not very clear, but the general idea is that non-Humeans assume fundamental laws have some character. Maybe it's a given, maybe it's kind of a priori or a priori assumption. And Humeans have to assume something about the mosaic, being cooperative, being susceptible to unification, susceptible to best systematization, and that we can discover. You can imagine we could live in many possible mosaics, metaphysically possible mosaics, they are not going to look that form. Although, Barry, I think, has an answer.
Yep, I just saw Barry's hand. Barry, go ahead.
Right.
Yeah, but look, Eddy, everybody has to have some sort of way of doing inductive reasoning.
Yeah.
So the Humean says, well, the mosaic we haven't seen is similar in whatever the appropriate ways in which induction works to what we've have seen so far. And the laws then will have to be, or not have to be, but they will be similar for the same reasons. Since they have to be simple by the very account of what laws are on the Humeanic view, the simplicity will be a guide to what the laws are. But on the other hand, as far as the non-Humean is concerned, well, induction might say that the Mosaic is similar to what it is so far, but the laws could be anything. They could be incredibly complicated as far as the nature of laws are concerned.
Yeah, thank you, Barry. So I understand where you're coming from, but the way I'm thinking about Humean scientific enterprise is not like assuming the Mosaic is regular, because we know that Humeans believe the Mosaic is not going to be regular or similar in the future. It's only similar insofar as being summarized by a simple law compatible with the present. So they're assuming, I think they should assume, that the best system compatible with our current evidence should be such that globally it should be so simple, can be summarized by some sentences or equations, like Einstein
I think of that differently. I think that's not an assumption about the Mosaic in the sense of it being a metaphysical assumption. It's an assumption about laws. And what the Humean should say is, look, if the Mosaic isn't sufficiently simple, there just aren't any laws.
Well, there still could be summaries. They're no more complicated than the Mosaic, and maybe simplifying in some regard. And if there are no laws, the question is still regard, why is there any law at all, right? So
I don't
that's the question
understand.
we can
If
ask
there's
for
a simple summary, it'll be a law.
Right. So I think the question is going to be parallel on Humeanism and non-Humeanism. So I'm not in this paper arguing that non-Humeans have advantage over non-Humeans. I'm saying that Humeans don't have advantage over non-Humeans. But of course, there can be differences in how we justify whatever principle that we need to get induction going. And maybe it looks somewhat continuous with the Humean metaphysics of lawhood. And it looks somewhat like an abrupt addition to the non-Humean metaphysics. I don't think it's like that kind of situation, but I think one might have this impression. And if so, then the question is, how should we think about the relative differences and similarity
Well, I
between
should have known I wasn't going to convince you. I did send you a long email, and then we can deal with it then. I did
Right.
already send an email. Okay.
I think I should be convinced after email by induction. But yeah, that's helpful. So the motivation I have written in this paper is exactly this, that many Humeans, and maybe non-Humeans too, think that there's an epistemic advantage on Humanism. I think that's not true. So part of this is to clarify what simplicity should look like for nomic realists, and part of this is to say that Humeans, no, we're on a par, at least with regard to simplistic physical laws.
No, I see your hand. Go ahead.
Well, you mentioned that you're primarily concerned with fundamental laws, but then thought that perhaps it would apply to special science laws. And I'm wondering with derived laws, I was trying to remember back to the discussion in Hempel as to how you distinguish accidental generalizations from genuine laws. And the kinds of examples he uses are things like everyone in this room has coins in their pockets as an accidental regularity. And so I was just thinking, well, if you contrast that with everyone in this room has carbon in their body, we might think that that is a biological law, a derived law. Not necessarily, I wouldn't have thought it's so obvious that it's simpler unless it's something about the simplicity of the predicates. I mean, carbon perhaps is simpler, but maybe then one could sort of amend his example to say, well, everyone in this room is within 1 meter of a cesium atom. That might be accidental regularity that just happens to be true. Not necessarily more complex than the biological one.
Yeah, good. So what I think someone might say is the carbon effect follows from simpler laws in biology. You can trace them back to where, with high probability in some sense, trace them back to simpler explanations. But the coin example, the coin effect will not. It follows from a low probability event from simpler laws. So in that case, one explained, the other is not explained by simple laws. But this is something related to what Barry has worked on and I've worked on connection between statistical mechanics and scientific explanation. How we think about derived facts, how do they relate to this picture of the world in which we have not only dynamical laws, but also boundary condition laws, such that they can give rise to probability effects of various contingent features. And some probability effects will be high probability effects, and some will be low probability effects.
Good. Can you give me a reference to that?
Oh yeah, maybe you can take a look at Barry's paper on the manticulus.
Oh, yes, yeah,
I'd like to start.
I do remember. I have another
Yeah,
note.
it's references to earlier works and other works.
Good, thanks.
Thank you.
So I just need another hand. Oh, another hand. Yes. Abdurrahman, go ahead.
Hello.
Did you have a question?
Are you asking me or somebody else?
Oh, I thought I saw. Oh, I must have seen the wrong hand. Anissa, go ahead, please.
Eddy, it's
Hi,
very
Lisa.
nice to meet you. Thank you. I really enjoyed your talk.
Thank you.
I've been very interested in laws and human interpretation of laws. I have two questions, one of which is for clarification, another is in search of consolation. The first is I would like to know how you're defining simplicity, and I may have missed it at the beginning. But on the one hand, you might say, for example, a Newtonian law of gravity is simpler than Einstein's interpretation of a law of gravity. Einstein's can be reduced, but it's inevitable that Newton's law is less authoritative. And so I was wondering if, and I mean, I also wouldn't say that Einstein's law is not simple. So I want to just know if using a definition of simplicity that was less similar to crudeness would resolve the problem you talked about.
Less simple to less crudeness, is that said?
Crudeness, so a little bit less of a blunt definition.
I see.
So for example, it's saying that Einstein's law is not more complicated than Newton's. It's just maybe Newton's is a little bit more blunt.
Oh, I see.
Does an alternative definition of simplicity resolve the problem you talked about in the middle of your presentation?
Yeah, thank you.
If I may just put a finger on that. So, I mean, the example you gave, Anissa, is exactly an example that Paul Dirac gives in his 1939 Scott Prize lecture. He specifically says, you know, simplicity isn't obviously the final answer because, you know, general relativity is more complicated than Newtonian gravity.
Right.
But it has greater mathematical beauty. That's what he elevates to the principle over simplicity. So this is a question with a great provenance.
Right. Yeah, it's a good question. Thank you. So the way I think about simplicity is that it is one of the many guides for lawhood. And another important guide is empirical adequacy. And it is what gets the first step in choosing the laws. If some law is not even empirically adequate, say not predicting right in orbital dynamics, so on, it's out. And we don't even have empirical equivalents. It's like we have just empirical falsification of theory. Now, if something is simple, in what sense is it simple? In the case of Newtonian gravity and Einsteinian gravity, I think it's a hard question, right? One unifying, one simply in mathematical form, but so I don't think there's going to be a determinate answer in every pair of judgments. We can have non-determinate answers for certain cases, but appeal to other virtues, other empirical virtues, say, to decide what is the right theory. The way I think about simplicity is very pluralistic. I think there are many good measures of simplicity and complexity: cosmograph, informational, computational, number of parameters, dimensional, maybe conceptual, and even syntactic simplicity. I can get that because I have naturalness on the side. So I have all this baskets of virtues, different specification of simplicity, and they have to trade off against each other. But I think the optimistic hope, and not unreasonable one, is that the good theories, the winner, is going to be so much better than the rest in terms of every one of those criterion, maybe most of those criteria, such that we don't have hard cases in the realist theories.
If I might rephrase my question, I find that a measure of simplicity is not the same as an alternative interpretation of simplicity. So, for example, you could talk about aesthetics as a measure of simplicity. You could talk about aesthetics as one way of understanding simplicity. So it is something more aesthetic than another, and it offers a clarity that makes it appear more simple. But you might measure aesthetics differently. You know, how long is your law? How many? You might have how beautiful it is. So,
how beautiful it is. I see.
Drawing more on Dirac. So you could ask, is it very long? Does that compromise how nice it is, how aesthetic it is?
Oh, I see.
Does it have a lot of square roots and makes it look a little ugly? So that would be a measure of how beautiful it is. But then in that case, you would be understanding beauty or aesthetics as simplicity. It offers clarity, it offers smoothness, as opposed to it's short and quick and clean. Do you understand what I mean? So simplicity, so one way of understanding simplicity is not the same as, in my eyes, as picking a measure of simplicity, because you could have different interpretations of what simplicity is, and then different measures for each of those understandings of simplicity.
I see.
So if
So
my question is not how would you measure simplicity, but what definition of simplicity are you using?
Right, I see. Yeah, I think I'm working with kind of pretty vague notion of simplicity, and I want this to be a pre-theoretical notion that can be made definite by different proposals what simplicity is in each domain. Say in tests of random laws or probabilistic laws, you might use one particular definition, the Kolmogorov definition of complexity, as a notion of simplicity. But in the case of, say, the Mandelbrot set, something I discussed in my paper with Charlie Goldstein and discussing Penrose's book, The Road to Reality, the beautiful kind of geometrical structure with very simple law. In that case, it's not algorithm. Well, it's algorithmic in some sense, but the beauty of this is not that it is short. It's more like it's surprising, right? Is that this complexity of the whole complex plane can be distilled into this very nice and simple formula. That's the surprisingness of that feature that's kind of making compelling. So I think Penrose has this quote that it's not just simplicity per se, but simplicity when it's unexpected.
So can I ask, when you're saying simplicity as a guide to lawhood, is that, is that the same as saying virtues as a guide to lawhood? Like, why would you not pick something more general, like the length, the kind of math you're doing in it? Why would you choose simplicity over saying we pick laws based on the virtues they offer us? What is it about simplicity, and what kind of simplicity are you looking for? So I'm looking for something, I mean, if you have a general notion of simplicity, that's absolutely fine, but then it's interchangeable with something like we pick the laws that have virtues for us.
Yeah, it's a good question. So on the side of being vague, then I lose definiteness, and it's hard to see how this differs from general feature that any law can work. Yes, good question. I don't know. I think there is a consensus maybe on which laws are simple and which laws are and let's see. So I think there's consensus on which laws exemplify simplicity, this virtue. Okay. So I do think that many other virtues, many other guides are also reasonable. That's why I say it's a fundamentalism guide, it's not the guide, right? So it's compatible with other things being also virtues or guide to lawhood. I want to emphasize on simplicity because it's often discussed in the literature, and it's very relevant to questions about induction or question about time-dependent laws, boundary condition laws, or different ways of thinking about the Mosaic and ontology and nomology. So all those discussions are focusing on simplicity itself. That's why simplicity is kind of a place where many things converge. But I do agree that there are many other virtues that can be guide to lawhood, like informativeness, strength, right? Or fit to data, or naturalness of the predicates involved.
So you're saying simplicity would be convergence, or I missed what the
simplicity is one feature that many debates in philosophy of physics converge to.
Okay, thank you very much.
Thank you.
So I don't see any other hands. I have a couple more questions. I think maybe we only have time for one. So toward the end of your slides, you started referring to statements or propositions or entities P.
Right.
That could be, you could ask, are they true or are they false? What's the probability that they're true or false? And then you had this other question, right? Which is, is it a law, right? This mapping from these elements P to L of P, and then you could ask, what's the probability that it is a law?
Yeah. And by the way, those P's are called subnomic propositions by Mark Land. So I didn't exactly about this. Sorry.
I was going to ask what you meant by them, because I know what I have a picture of what they could mean in the non-Humean account. For example, the non-Humean account, you might notice, look, there's an equation out there, and it's it's an equation that relates, the density of this substance to the rate of activity in this substance. Or it could be a statement like Noah made, right? That we all have coins in our pockets, or that we're close to cesium atoms. And maybe one of those statements is the Lagrangian of the Standard Model, or something like that, right?
Exactly.
And so there's this additional question over and above the truthfulness of those things, right? Because those all may be true.
Yeah.
But there's this over and above question, okay, but which of them has a high probability to be a law?
Right.
I think I understand that in the non-human account.
I see.
Where I'm having difficulties understanding what that means in the human account, because in the human account, right, you have a collection of things that you're putting into your best systems account. And it seems like this consists of these subnomic, I didn't catch what you said, subnomic, what was it?
Propositions.
Subnomic propositions. Then maybe there's a collection of these subnomic propositions, and then the Humean has this, again, over and above task of having to identify which of those have a high probability to be a law. But I guess where I'm not quite understanding is I feel like a Humean simply would not put anything into the best systems account that's not a law, right? All the things the Humean is going to put in are going to be things that they think are laws. That's part of what it means to have a best systems account.
Well,
so
usually there is derived consequences and actions.
Sure. Yes. So I guess this is exactly my point of confusion, and where I wasn't seeing, to the extent that you can make a claim that a best systems account contains lots of ingredients, and then you have this additional task of having to identify with what evidentiary probability, some of them are laws and some of them are not, then the Humean is, I agree, a similar situation to the non-Humean. But I guess my question is, I'm not sure Humeans would agree that that's how the best systems accounts work. But I could be mistaken.
I see. Yeah.
You only put things in that you already think are going to be laws to the best systems account, but maybe I'm mistaken. I could be misreading it.
That's a God's perspective. If you have the whole mosaic, you know which facts are true, and then just put it in the most best system. Yeah, but we are not in God's perspective. We are in local agents. We have direct observation only a small part of the mosaic. So we're testing theories. We're trying different guesses when having different hypotheses what the mosaic is like. Basically, test different laws.
So you're saying basically a Humean is going to collect all these facts together, construct a best systems account, but then because they don't know everything, they have the same task of having to figure out which things.
Way. The best system supervenes on the micro detail of the mosaic. You don't directly observe the micro detail. So I think Bear has a very nice paper who talks about you start from the middle. You start from the middle, medium-sized dry goods, tables, chairs, pointers. You do experiments. You test what theories are good, and then hypothesize: is it continuous spacetime, discrete spacetime? Is it Minkowski, Newtonian? And those things are not something we directly observe. It's more like theoretical inferential beliefs we have from what we think are good candidates for laws, which ones are more likely to be the best system of the actual mosaic, even though we don't have any idea of what actual mosaic is like. I have some idea, but not a complete idea. The actual mosaic is fine-grained, microscopic, and complete. We are coarse-grained and partial. So the probability is, Humeans and non-Humeans are going to do science exactly the same way, I think, at least BSA and MP. They're not going to say, okay, I'm a Humean, so I first direct observe every particle position in my chunk of spacetime and do the best system from my chunk and then generalize. Oh, no, that's not how we do Humean science either. You start from the middle.
Great. All right, we're going to have to leave it there because we're at the hour and I want to respect everybody's time. But thank you so much, Eddy. This was an amazing talk and an amazing discussion and question and answer. Thanks to everybody for sharing your time with us. As I mentioned, the seminar series is going to be taking a winter break, and we'll be coming back again in February. So please stay tuned for announcements with updates. The video recording of this seminar and the discussion and question and answer is going to be posted to the YouTube channel shortly. Again, thanks to everybody. Thanks again to Eddy, and please see Eddy's paper, which is really great. It'll be posted. A link will be posted to the seminar series website. Until we meet again, be well, be safe, be healthy, everybody. It's good to see you all.
Thank you so much for organizing, Jacob. Thank you, everyone, for coming and questions and comments. Very helpful.